Have you ever heard the saying, one person's trash is another person's treasure? Well, the same is true for our galaxy. One astronomer's trash is another astronomer's treasure. And today I'm going to tell you a little bit about a project I'm proposing to take the trash in my research and turn it into treasure. So what is my research? I'm in charge of creating the third dataset for the International Pulsar Timing Array, which is an international collaboration of hundreds of scientists all around the world. And what the International Pulsar Timing Array, or IPTA, is trying to do is to detect low-frequency gravitational waves using what we call pulsars. Pulsars are something that's really interesting, and we'll talk about them in a minute. But for right now, let's talk about what a low-frequency gravitational wave is, because that's kind of weird. Imagine the entire universe was a pond, and you dropped a rock in the pond. What would happen? There would be ripples going out from where you dropped the rock, and the size and shape of the ripples might change based on how big the rock was. In the same way, if we think of the pond as being the fabric of space and time, and the ripples, and the rock as being a very large black hole we call a supermassive black hole, we could create ripples by taking two very large black holes, millions of times as heavy as our sun, and starting to smush them together. This process takes a very long time, much too long for us to observe, but it does create these very low frequency, very large waves that head outwards from the space where our two millions of times heavier than the sun black holes are starting to collide. This kind of collision mostly happens when two galaxies are merging together. And these ripples will travel all the way through the universe towards Earth. And in principle, we can detect them. But how? Well, when you're detecting gravitational waves from smaller objects, what you do is usually this kind of cool sci-fi process involving lasers and vacuums, and you have these vacuum arms that are a couple miles long. The problem is the heavier the object you're looking for, the longer your arm needs to be. So if you figure you want something millions of times heavier than the sun instead of something 10 times heavier than the sun, you're going to need a pretty big arm. So we don't even try to build one. Instead, we use very stable objects throughout the universe, i.e. our pulsars, to tell us about what is happening. So that we look for signals that a wave has passed by these really stable objects and use those to find our gravitational waves. So we need to observe our pulsars. What is a pulsar? Well, it's a very small, very dense object that's formed after a medium-sized star comes to the end of its life. So when a medium-sized star gets to the end of its life, it explodes like a drama queen. And we call that a supernova. And most of that material just kind of blows away. But a small portion of it collapses back down and forms a pulsar, something that is maybe 10 miles across and weighs as much as 1 or 2 times the sun. Now, why do we call it a pulsar? Well, these really dense objects have a beam of light sticking out one axis. But on a slightly different axis that doesn't line up with the beam of light, they're spinning. So what happens from our perspective is we see the pulsar and then we don't see it. And then we see it, and then we don't see it. And it looks like it's blinking on and off. It isn't really blinking on and off. It's just spinning like a lighthouse. But from our perspective, it looks like it's pulsing, so we call it a pulsar. Now, there's a subset of these pulsars called millisecond pulsars that are known for being incredibly stable. They spin much faster than other pulsars, hundreds of times every second. And we're able to predict their spin with accuracy in the hundreds of nanoseconds. So basically, take a decimal point, put like 7 zeros, and then a 1. That's how precise we can be in predicting the spin of these pulsars. And these sorts of objects are precise enough that if we get a bunch of them together, we can actually see when these big ripples in space-time pass through. So how do we get information about predicting what's going on with the pulsar spin? Well, we need to create something we call a timing solution. And there's 3 big classes of things that go in a timing solution. The first is things that happen at the pulsar, so on the left of our cartoon. That's the pulsar spin, how fast the spin is slowing, if it's got another star there that it's in a binary system with, how they interact, that kind of thing. And on the right-hand side, we have things that are related to the fact that we are observing with radio telescopes on the Earth, something that is in a particular place in our Milky Way. So we might need to worry about the movement of the Earth relative to the pulsar, or things that happen because of our sun, and that sort of thing. And then there's everything that happens in the middle. Now, we think of space as being empty, and that's basically true. But there's empty and then there's empty. The interstellar medium, or space, is really full of big clouds of gas and dust. And we're particularly worried about something called ionized gas, which is basically just gas with an electric charge. The reason why we're worried about that is because it does something called dispersing the signals from the pulsar. So what happens is you have a beam of light from your pulsar, and it's going through space, and it hits this cloud of gas and dust, and it actually gets slowed down by the electrons in the cloud of gas and dust. But it doesn't get slowed down at all the same rate. The higher frequency, or say the bluer parts of our light, are slowed down a little bit less than the lower frequency or the redder parts of our light. And so the signals arrive at our telescope at different times. And that gives us a characteristic swoop in our data. Now we know that can't be right because all of the data must have left, all the light left the pulsar at the same time. And so we can take that swoop out, and we call that de-dispersing, because we call the swoop the amount of dispersion. So after we've de-dispersed our pulsar, we get a number for how much we had to change it, and we call that the dispersion measure. So it might be, say, 20 parsecs per centimeter cubed, where parsecs per centimeter cubed is just a unit of distance per volume. So we have this value, and for most applications, we're now done. The problem is we're specifically looking for super, super precise pulsar timing solutions. And that means we have to think about not just what the total amount of dispersion is, but if it's varied at all. And so we might know our value is around 20, but we might be worried about variations that are like 0.001. We need some kind of metric to model these, and we need to use that model to make sure we have the most precise timing solution we possibly can. Now, to date, we've mostly done this in a rather ad hoc way. Either we've just said, okay, let's just jot down each day how much we're not at our nominal dispersion measure, or we've said, let's fit a noise process to this, things that are effective, but aren't particularly based on what's actually happening in the interstellar medium. What I'm proposing to do is to change that, to bring together people who are expert pulsar timers and people who understand the interstellar medium, along with people who are really good at computational modeling, particularly something called Gaussian process modeling that is ideal for modeling what basically random processes. And bring these three groups of people together to create a new model that's more computationally efficient, that's more physically motivated based on what's really happening in our universe, and that models our dispersion measure better so that we can have a more precise timing solution. Now, these dispersion measure variations are essentially trash in our data. I don't want them. I want them gone. That's the whole thing. But I also have this extremely comprehensive set of them. All this information about what's been happening in the interstellar medium over the past 20 years for a total of about 80 pulsars in my IPTA data set. So this is a lot of usable information. And so once I've created a more interesting, robust, and physically motivated model, I can then give that model back to the interstellar medium experts and ask them, so what kind of science can you learn from this? And they'll be very excited, and they'll open up their treasure box and say, oh, here's something interesting. And we can create more science from the same data without actually having to collect any more data than we already have. Now, how am I going to do this? I'm going to do this a bunch of different ways. One way is by just making it a priority, making this something that's important to us as we collect our data or as we analyze it. And I'm also going to bring together a group of people physically in a busy week. I'm going to invite a bunch of people together to sit down and talk about how we can bring together all these different concepts to create the very best models we can and turn one person's trash into another person's treasure. Thank you.